All right, gravimetric analysis. So in the first step, it's going to have you calculate the concentration of the zinc in the original solution. And this is standard, standard stoichiometry. Standard stoichiometry is usually grams to grams, but we can easily, once we go to moles, we can do all the steps. So in here it breaks it down into the individual parts. All right, and usually it's like that: A, and then B is the next, C, and so on. So let's look at that in more detail. So you're going to say calculate the mass of the zinc carbonate. So you're going to weigh filter paper that has the zinc carbonate and water. As the water is driven off, then you're just going to have the filter paper and zinc carbonate. So to find the mass of the zinc carbonate, you take that mass of the combination that's dry and subtract the starting mass of the filter paper. So then, now, so I should have gone here. So what we have then is we have the zinc and the sodium carbonate you mix together. And you're producing the zinc carbonate. That's what we're weighing, right? That's what we're following. So it's telling us then how many moles of the product that we have. And so that's to get to moles, we go grams and grams to mole. And now that we know how many moles of product, we can relate this back to the moles of the reactant. And so we're able to find how many moles of the zinc from the zinc nitrate were there. And this comes from the balanced equation. Now to go to the concentration, all we have to do is think about what is molarity. It's moles per liters. And then, so we need to take those moles and divide it by the volume. And the question is which volume? Do we take the total volume or the volume of the zinc? And the question is what is the concentration we're trying to find? We're trying to find the concentration in the original zinc nitrate solution. So we know the moles, and then we're going to divide that by the volume. All those moles came from the volume, and so it's the volume that you pipetted the zinc in. So now the second one is confirm whether the sodium carbonate was in excess. Use the concentrations of the solution to determine how many moles and confirm it was in excess. So from the first one, you got the moles of the reactant, and now all we need to do is find the moles of the sodium carbonate by using volume times concentration gives you moles. And so if we compare these moles, this should be bigger than this. And why is that important? Well, because we're going to get some solid here, and we can just do some numbers. But then in order to say that this is a valid experiment, this is the check we need to do. So if this is in excess, that means that this is the limiting reagent. So the amount of product that we got here is limited by how many moles were in the zinc nitrate. And that allows us to solve for this concentration. Afterwards, if we find out it's not the case, that this is not in excess, that means we don't have a valid result. So therefore, we can't draw conclusions based on our data. So that's the importance of it. All right, number 3, use the following steps to calculate the formula of the cobalt chloride hydrate. So this is what you can do while you're drying your reaction. So again, what's the mass of the water that evaporated? Well, what are you measuring on from the data? Like you're given numbers just like they used to do in the lab instead of thinking about it. So you can make a plot of it and kind of follow it. You can do that later, I think. So here we're trying to find out how much water evaporated. So we're trying to see how much went away. So we start and we have a hydrate. When we heat it up, then we drive off the water as gas. All right. So the only solid left behind is this. So we have the solid here in the beginning. And then at the end, we have this number. And so the difference between those two is going to tell us how much mass was lost from the water. All right. So now it says how many moles of water. So how do we go from grams to moles? We divide by the molar mass. So since you know the grams here, you're going to convert grams to moles. Now calculate the moles of the dry copper chloride. Is it copper or cobalt? No. Here, mix the two. You fix that. So here you have it in 2, there's no hydrate, it's just that. So just like in the first one, you have grams And so we can convert this grams to moles by dividing by the molar mass of it. All right. Now calculate how many waters per chloride were present. All right. So we can do the ratios between these two numbers and find it. All right. So that's what we're trying to find. What is this X here? So this should be some multiple. If it's 1 to 1, then it's easy. This is the same number. If this is 2 to 1, then that's 2 and so on. So you simply divide the bigger number by the smaller and find out, because this should be bigger. All right, the hydrate change color and the visual observation can be useful property. There are several hydrates for this. Research the difference in properties that could be used to support the formula you deduced. All right, and so this is actually very common. We try to look for clues that either things aren't following our hypothesis about the change or they're supported. And so you just want to collect as much data. So there's a lot of properties on here, but there's one useful property that's related to the color. One source of error would be that not all the water was driven off during heating. Create a graph showing how the mass of the sample changed during heating, then use your graph and explain whether the sample was likely completely dehydrated or not. All right, so you're going to make a graph of the data and you want to show it. And whenever you plot it, you might have numbers and they kind of go like this, and you have a bunch of white space by default on the cell. So what you want to do is you really want to see, is this trend continuing down or is it flat? If you zoom out, it'll look like it's flat. So what you should do then is, instead of doing this where you have all this wasted space here, is you want to zoom in and make a plot that uses the whole area. All right. So zoom in, don't change, adjust the y-axis, don't start at 0, and really allow you to focus on that trend to see whether it's flat or not. Number 6, create a nice table of your data. You have a bunch of data. Usually this one is kind of the first one, can be a random kind of thing. We want you to organize your data and results into a nice table. You can do it hand-drawn or in Excel. But either way, we want you to kind of think about submitting your raw data and your results, that you can do it in one table or use the multiple tables here to kind of give that. Number 7, explain how one of the activities would affect the concentration if the beaker was wet or dry, or some of the sample bumped off the filter paper. You might see this. So that should be relatively easy for you. If you already done the calculations, you can kind of substitute the numbers if you don't know and see how they would change and so on. On a side note here, let's say you did lose a little bit of sample then during the course of the reaction. So what I would do is make a note where it fell off and then just kind of record the magnitude of it. Was it like 1% of the sample, 5%, 50%, those kinds of things? Because in the real world, I mean, of course, the data is not as accurate, but it's not a total waste, all right, at the same time. So still trying to record it. The same thing whenever you're trying to remove some solid from your beaker. Here we filtered, and let's say you left behind some solid in there. That last little bit can introduce the most error because you're going to wash with a bunch of stuff and blah, blah, blah. So what I would do then is to just record a note. How much did I think I left behind? Like 1%, 2%, and so on. And the first time you do an experiment, you just want to see if stuff works and gives you an idea. I wouldn't waste my time on perfection and so on. So, and now the last one here, copper's versatile. Suppose you have this many grams of copper sulfate and this many grams of iron. What yield would you expect? So here, what you have to do, if you haven't seen this in class, is you have to do 2 reactions. So you have copper going to form either product, but since we're going to get we're asking what the yield of the copper would be. That's what we would go to. So using this value, we'd calculate how much, use this value and calculate. And one of them is going to be more than the other. And so that's the one in excess. The smaller one is what you're looking for. So the smaller and the larger. All right, you're going to look for the smaller one. That's what we call the limiting reagent. And it dictates the yield. All right. So nice, fun stoichiometry. That's always fun. But that's it. That's the lab.